We call it the G word, a word that you're not allowed to say in public.
This is Hugh Hunt. He's Deputy Director of the Centre for Climate Repair at the University of Cambridge in the UK. The G word he's referring to is geoengineering.
The geoengineering is how can you modify the climate for the purposes of reversing the effects of climate change. But the word has become associated with the sort of the nasty sides of geoengineering.
Our planet has endured 11 straight months of record-breaking heat.
Well, Bangladesh is seeing its highest temperatures in almost 60 years.
Devastating fires outside Athens claimed one life, forced thousands to flee their homes.
Fires broke out in central Chile and have left over 1,600 people without homes.
Global temperature records are being broken month after month. And some of the world's worst natural disasters in recorded history are taking place around us. You might think that any technological developments with the potential to stop global warming would be welcomed around the world. But the pursuit of human-made climate modification is a hugely divisive issue. So divisive that we decided to explore the debate on climate geoengineering in 2 episodes. We'll hear from experts carrying out research into what's possible and those deeply opposed to the very idea of it. In this first episode, we'll explore the science behind different geoengineering methods and the projects currently going on to research how they might work in the real world. In our second episode, we'll speak to researchers mounting a campaign to stop a particular type of geoengineering called solar radiation modification and why they're so worried about it. I'm Gemma Ware, and this is The Conversation Weekly, the world explained by experts. I'm joined to start this episode by the Environment and Climate Editor at The Conversation in the US, Stacy Morford. Welcome back to the podcast, Stacy.
Thanks. It's an important topic.
It is. And Stacy, this idea of using geoengineering techniques to modify the climate is getting a lot of attention right now, but it's been around for a while. So what's the history of climate engineering?
So humans have been looking for ways to manipulate the climate and weather for centuries. But the origin of geoengineering is generally traced back to the middle of the 20th century. After World War II, a lot of scientists were interested in using new technologies to improve conditions for people, particularly for farming. One of the early examples is cloud seeding, which involves shooting particles into storm clouds to try to get a little more snow out of them. But the geoengineering that we're talking about today is very different. Many scientists believe that large-scale geoengineering experiments, like reflecting more of the sun's radiation away from the Earth, could lower global temperatures and slow climate change. The problem is that no one fully understands the global repercussions. While some countries might benefit, there are real concerns that others could see worsening storms or drought as a consequence. And when people can blame their neighbors' geoengineering experiments for disaster, that can spiral into conflict.
It's almost like something out of a science fiction novel or a superhero comic, isn't it? Where the villain has a giant weather machine or something.
Yeah. You know, the idea of one person or a country being in control of something that could have really dramatic consequences for our planet is scary. But we're already seeing deeply concerning threats from climate change, too.
There's a lot to weigh up here, and that's what we'll be delving into in these 2 episodes, into the controversies and the science around geoengineering. But thank you, Stacey, for setting out the context for us.
My pleasure.
Hugh Hunt trained as an engineer.
Well, I used to work mainly in noise and vibration, how to make trains quieter and stop noise from getting into buildings.
But a little over a decade ago, he got involved in some consultancy on a climate engineering project.
And then I thought, you know what? In 20 years' time, my kids aren't going to be caring terribly much whether their trains are quieter. I'll probably care more about whether the Arctic is still frozen. So I switched subjects, really, and since then I've been working in climate repair.
When I asked Hugh to lay out the case for geoengineering the climate, he told me about a diagram that sums it up for him.
If you go to your favorite search engine and type in napkin diagram, you would be forgiven for being surprised that up comes a really quite a serious thing about climate change, the very first thing. And the diagram was first drawn by a chap called John Shepherd, maybe 15, 20 years ago.
If you don't have a moment to pull this up in your browser, I'll describe it for you. It's a simple-looking graph. On the vertical axis is temperature in degrees Celsius. On the horizontal axis is time in centuries, starting at around 2000. 3 lines predicting different scenarios extend upwards, showing Earth's temperature rising.
There's a line which goes shooting upwards, business as usual, the temperature keeps on rising.
The second line predicts a scenario where fossil fuel emissions are reduced from around now.
If we cut emissions aggressively, then that temperature will stabilise. But at the rate we're going, it might stabilise at 4 degrees, 6 degrees above where we are, which is no good. So then the next line is carbon dioxide removal, which we need to do to get the carbon dioxide out of the atmosphere. But that might take another century or two to get down to our magic 1.5 degrees.
According to the UN's Intergovernmental Panel on Climate Change, the IPCC, staying below a 1.5 degree increase in overall global temperature from pre-industrial levels is necessary to forestall the catastrophic consequences of human-caused global warming. The napkin diagram suggests that aggressive emissions reductions, combined with mass carbon dioxide removal, could take temperatures back below 1.5 degrees by around 2300.
And then what do we do in the meantime? For the next 150 years, there's that sort of bump that we'll have created. We'll have gone over 1.5 by quite some significant margin, perhaps 2.5 or 3.5 or 5 degrees warmer than now. And then once we get our emissions cut and we get our carbon dioxide removal, well, that's great, but that's not for another 150 years, and the Arctic ice will have melted and the Antarctic glaciers will be irreversibly damaged.
On the diagram, this bump is shaded in and labelled solar geoengineering with a question mark next to it. Now, we'll be getting into the science of solar geoengineering later in this episode and in our next episode. But essentially, what the diagram suggests is that by attempting to alter the amount of solar radiation trapped in the Earth's atmosphere, that 1.5 degree threshold could be arrived at decades earlier than it would otherwise.
So this solar geoengineering is this band-aid, this thing we need to do to buy us time.
So what are the potential ways of geoengineering the climate? Scientists argue that there are 2 ways to reduce global warming. One is to increase the amount of heat radiated from the Earth's surface that escapes into space. This includes decreasing our use of fossil fuels, which emit carbon into the atmosphere, trapping heat on the Earth's surface. The other method is to increase the amount of sunlight reflected back into space before it lands on something on Earth and is converted to heat. At Cambridge, Hugh Hunt and his colleague Shaun Fitzgerald are leading a team of scientists exploring potential geoengineering strategies to reduce global warming from both of these angles. Shaun is also an engineer by training, and he's the director of the Centre for Climate Repair, where Hugh is the deputy director. One of their current projects that's getting some attention is in the Arctic Circle. Shaun explained it to me.
We are looking at whether we can get more sea ice in the Arctic, especially in the Arctic summer. So whether we can create a way of not just preserving, but ideally extending the sea ice cover over the Arctic. And the sea ice forms naturally in the Arctic winter after about September. Basically, the nights are drawing in and it's getting pretty cold. And then when the sea ice forms, we all know that ice is less dense than water, so the sea ice forms on top of the water. And this is really important because any new ice that then forms after you've had a skin of ice then already in place, that new ice forms on the underside of the existing ice. And the freezing process releases something called the latent heat of solidification, probably something we all learned when we were at school.
For those of us who may have missed that particular chemistry lesson, the latent heat of solidification is energy released or absorbed by a system as that system changes state. So in this case, it's a body of water going from a liquid state to a solid state, ice. As the ice freezes, the temperature of the overall system remains constant, and the heat is conducted through the ice and radiates out into space.
But ice is a pretty good insulator. So as the ice thickens, the rate at which you can get heat to be conducted through that ice layer decreases. What that means is, everything else being equal, the rate at which new ice forms decreases as the ice thickens. So the big idea is, instead of just putting up with the fact that you've got this insulating layer, is to pump seawater on top of the sea ice and get the freezing process to occur on top of the sea ice.
The second related idea also involves pumping seawater on top of the sea ice. In this case, the scientists are trying to eliminate the snow on top of the ice. That snow serves as an insulating barrier, causing snow-covered ice to retain more heat than just ice on its own.
So pumping seawater on top of the sea ice, but this time only pumping enough to fill the little air voids within the snow with water, allow that to freeze and become a solid ice layer, and then you've just got pure ice rather than ice and snow, and pure ice is more conductive.
This pure ice then allows for more heat to escape, and the lower temperature enhances the natural process of ice forming on the underside of the sea ice during the Arctic winter. Now, while both of these ideas involve pumping water over sea ice, they have different potential side effects.
The amount of pumping that you need to do for a given accumulation of ice is less if you're using what we call the snow flooding idea. Also, the quality of the ice that you then end up forming is different, because the ice that forms naturally on the underside of existing ice is really crystals of H2O that form, and any resulting brine then, because it's dense, falls back into the ocean. Whereas if you're pumping seawater on top of sea ice for the express intention of getting more ice to form on top, the big question is, what happens to the brine? Have you actually created thicker but saltier ice? Actually, have you made things worse? In other words, because the melting temperature of salty ice is lower than the melting temperature of regular ice, it'll start to melt earlier. And actually, as a result of pumping seawater on top of sea ice, there is a big question that because you are reducing the rate of accumulation of natural ice on the bottom, you may have made things worse, but we don't know that yet. And that's why we're doing research into both of these ideas and doing numerical modelling. We're doing experiments in the cold rooms here at the University of Cambridge and also doing field work.
After years of theoretical study, the first real-life experiments are now taking place. Shaun and his colleagues are collaborating with a London-based not-for-profit startup called Real Ice. After making some observations of ice in Alaska a couple of years ago, in January 2024, during the Arctic winter, they began a pilot study up in Cambridge Bay in the Arctic Circle in northern Canada. With the agreement of local residents, the team pumped seawater over about 4,000 square metres of snow. 4 months later, in May, they returned to measure the depth of the sea ice in that area and in a control area.
And what they found was that the ice depth was 50 centimetres greater in the area where they had flooded the snow compared with the control region.
Shaun explained that this was split between around 25 centimetres of additional ice as a result of the freezing of salt water in the overlying snow, and a further 25 centimetres that had accumulated on the underside of the ice.
So the initial observations are pretty exciting, but therefore next winter we're going to do a much larger suite of experiments in a more programmatic way, looking at different permutations of how much you flood. Do you flood the snow? Do you allow the snow to come back?
As well as these sea ice projects, another significant area of research at the centre is called solar radiation modification, or solar radiation management, known as SRM. This entails reducing the amount of radiation that reaches Earth in order to reduce global temperatures. The centre is looking into multiple methods of SRM, and one of these methods involves what Shaun was just describing, allowing the snow to come back on the top of the Arctic ice.
The snow is more reflected than the ice, so when it comes to the summer, having a tiny bit of snow on the top can actually be really quite protective in the polar regions, especially the Arctic, where it can shine for 24/7 in the summer. The difference in the reflectivity between ice, and especially snow-covered ice, and just the dark ocean is enormous.
There are two other main strategies for solar radiation management, each aiming to reflect the sun's radiation back out of the atmosphere. One is called stratospheric aerosol injection. This involves releasing particles of sulfur dioxide or titanium dioxide high up in the stratosphere, roughly 20 kilometres or 12.5 miles above the Earth. The idea is that these particles will then disperse and reflect sunlight, potentially cooling the Earth. The inspiration comes from scientific observations of the aftermath of volcanic eruptions.
There is a very well-known set of observations, which was when Mount Pinatubo erupted in 1991.
The eruption of Mount Pinatubo in the Philippines in June 1991 was the second biggest volcanic eruption in the 20th century, and it killed more than 800 people, displacing tens of thousands of others.
It ejected something between 15 to 20 million tons of sulfur dioxide into the stratosphere, and the Earth cooled by about 0.5 degrees centigrade for over a year, 1 to 2 years. This was an observation. Clearly, it's no longer being cooled to that degree because the sulfur dioxide doesn't stay up there forever, but it stayed up there for quite some period of time.
The other method of SRM is called marine cloud brightening, and this took its initial inspiration from ships actually polluting the air over the ocean back when they used to have sulfur in their fuel. It turns out that these clouds reflected sunlight back out into the atmosphere, helping to keep global temperatures down. Here's Hugh Hunt again.
So no matter how much there might be good reason to put the sulfur back into shipping fuel, I don't think anyone will want to, because air quality is important. So what can you put in instead? Turns out that just ordinary saltwater spray. At sea, nature makes clouds by, when there's wind, you get waves, and when there's waves, you get sea spray, and when you get sea spray, you get salt in the atmosphere, and the salt in the atmosphere drifts up into the clouds and nucleates the clouds.
Nucleation is the process of raindrops forming around a particle, in this case salt. And so marine cloud brightening done via geoengineering involves using cannons to spray a fine mist of salt water off the back of ships.
We can create a spray, and this little salt crystals make their way up into the clouds, and we can make the clouds whiter and last for longer. And they're doing that as we speak in the Great Barrier Reef in Queensland in Australia to try and cool the waters around the Great Barrier Reef.
At Cambridge, the team are experimenting with the nozzle used to spray the water off the back of boats.
Try to engineer these nozzles to make droplets that are not 500 microns in size, but maybe a tenth of that, and they're 50 nanometers inside. And that for every droplet, we can create 1,000 times as many with the same amount of water. And that means when they get into the clouds, you get 1,000 times as many cloud droplets. And smaller droplets are whiter. More droplets means bigger clouds. And it takes longer for the droplets to get bigger to produce rain, so the clouds stay there for longer. So they're whiter, they're bigger, and they last longer. And if we can do that at sea and in the Arctic, well, that helps to cool the sea and cool the Arctic.
Geoengineering, and SRM in particular, are highly controversial ideas. Proposals to deliberately alter the Earth's climate raise significant ethical, environmental, and political concerns. Even among scientists who are actively researching SRM, there's debate about its potential risks and benefits. Some are unsure whether it should ever be put into practice, despite the potential to mitigate the impacts of climate change. One such scientist is Ben Kravitz.
So one of the things that I often say when I talk about this is geoengineering is terrifying. And if you agree with that, congratulations, it means you have a pulse. But there's one thing that scares me even more than geoengineering, and that's climate change.
Ben is an associate professor in the Department of Earth and Atmospheric Sciences at Indiana University in the US. He works with climate models to test the feasibility and potential effectiveness of solar radiation management.
From all of the climate modeling and natural science research that we've done, the conclusion is, by and large, it's not a perfect offset for carbon dioxide, so it's not a replacement for reducing our emissions, but by and large, for most people, a little bit of geoengineering is helpful. Now, when you get into social implications, that's where things start to get a lot more messy, because the world of humans is fairly messy.
Part of the messiness is determining who actually gets to make decisions about implementing something like stratospheric aerosol injection, which is essentially dimming the sun, and who might be excluded from those conversations. It's something Ben has published research on. We
know that cooling the planet by about 1 degree Celsius would require somewhere between $10 and $100 billion a year. I don't have that. I can think of a few very rich people who do have that, but they'd be bankrupt within a few years if they did it on their own. But those sorts of numbers are well within the reach of many countries or coalitions of countries. I'm not very good at predicting the future, so I'm not sure exactly who would want to do it or who would want to prevent it being done and then would try to stop them. And you can see where the geopolitics really starts to get in. But it is within the reach of quite a few people.
Say one country decided that they would go first and they really wanted to do it. Maybe they'll tell the world, maybe they won't. What are the national security risks if one country decides to go it alone?
So I think that they would tell people because it's really hard to think about doing this in a clandestine way. So the amount of air traffic you would need to loft that much stuff up into the stratosphere would be another large airport. And so you couple that with all of the mining or manufacturing that you would need to create the particles that would reflect sunlight. You're talking about a major industrial and transportation operation that's just impossible to hide. So there's no advantage to trying to keep it a secret. But in terms of the risks, presumably whoever decides to do it will be doing it for a particular reason because they're having problems with climate change. It might be heat waves, it might be droughts, it might be floods, various things. And so the question is, do they just say, we're doing this? Or do they say, hey, this is what we want to do. Does this sound okay to you? There are many different responses they could take that might elicit different responses all over the world.
If one country does decide to pull the trigger on this, the effects wouldn't be limited to within its borders.
You can't put a wall up in the atmosphere, and if you put reflective particles up in one place, they're going to go a lot of places, which there are advantages and disadvantages to that. An advantage would be only one country needs to invest for everybody to benefit. And a disadvantage would be if you don't like what's being done, it's kind of hard to stop it because the particles would go everywhere. Everything in the atmosphere is connected. It all talks to each other. And so it would affect many other places.
What about if it was an individual, say a billionaire or a private company who just said, you know what, I've got tens of billions of dollars and I want to put this into this technology. What risks would that bring?
So in terms of actual deployment, we live in a world of nation states. So any billionaire is a citizen of somewhere. And so that country is responsible for them. But in terms of other risks, so there's an issue of transparency. So if governments are doing these sorts of things, there are certain laws about transparency of what activities they're doing, what regulations they have to follow. There's a lot of shielding for private individuals or foundations or what have you. So there's less certainty about what's going on or what's being prioritized.
When we talk about national security risks, we're not necessarily just talking about kind of war, geopolitical risks. There are obviously other risks involved around food production, around people's livelihoods. Are there any types of geoengineering where the risks to that might be greater?
I would say we don't know. And I like that you brought that up. So that's one of the reasons I got interested in national security. I'm not interested in wars and bombs and things like that. I'm interested in, do people have enough food and water? Or one of the biggest ones out there is climate refugees and forced migration. If sea level rises and you're living on the coast, you can't live there anymore. And all of those present risks that I would say are very difficult to understand and are poorly quantified. But those are some of the things that people worry about the most.
That said, Ben points out that geoengineering isn't the only potential threat to people's livelihoods.
It's really important to remember that climate change is causing a lot of risks too. And it is entirely possible that geoengineering would alleviate some of those risks and also possibly introduce new risks. And that's the sort of calculus that we really need to get a handle on if people are going to make an informed decision about whether we should do this.
I guess my final question then is, has thinking about all these risks and the work you've done on them alongside your climate modelling work tipped the balance for you on whether you think this is something that should be pursued or not?
I don't have a good answer for that, but I can tell you about what my students think. I teach a course on climate change science, and at the beginning, I do a pre-test. I ask them, if you're concerned about climate change, why? If you're not concerned about climate change, why not? Or if you don't know anything, what do you want to learn in this class? And so I have 25 students, and the first time I did this, I was expecting a mix of responses here and there. I got, out of the 25, 23 students who basically said, I don't even know why I'm getting a degree because we'll all be dead in 20 years. I had to basically restructure how I was going to do the class to give students hope that, no, you're not going to die in 20 years. There's still time to do the things you want to do and live a good life and also help out with solving climate change. And as part of that, I do a day on geoengineering. So not enough to go into the huge amount of details. I don't sugarcoat it. I try to present it as neutrally as possible. And then what I hear from my students is, I don't necessarily like this idea, but thank God there's something.
And is that where you sit too?
I haven't decided yet. I don't want to give you an answer because it'll change next week. I'm still trying to figure that out. Geoengineering is not a solution to climate change. The solution to climate change is we need to stop putting greenhouse gases in the atmosphere. But maybe it could help.
Thank you so much, Ben, for coming on and sharing your research with us.
Yeah, thanks very much.
Elsewhere around the world, other researchers are also raising alarm bells about solar radiation management.
I worry that if people like me don't raise their voices and call these people out, Africa will ultimately be one of the continents that will be targeted for a rogue testing of SRM technology.
Every ton of carbon dioxide emitted while we're talking about SRM is a huge problem. That's a risk we just simply cannot afford to take, especially given that this may not be the panacea that some might think it would.
Listen tomorrow to our next episode of The Conversation Weekly as we delve further into some of the objections and complications to solar radiation management. Thanks to Hugh Hunt, Shaun Fitzgerald and Ben Kravitz for speaking to us for this episode. We'll put a few links in our show notes to articles that they've written on The Conversation. And thanks to our colleague Stacy Morford at The Conversation in the US, who you heard at the top of this show. This episode was written and produced by Katie Flood, with production assistance from Mend Mariwany. Sound design was by Michelle Macklem, and our theme music is by Neeta Sarl. Stephen Kahn is our global executive editor, and I'm Gemma Ware, the show's executive producer. You can connect with us on Instagram at theconversation.com or email us directly at podcast@theconversation.com. You can sign up for The Conversation's free daily newsletter by clicking on the link in our show notes. And if you like what we do, please support our podcast and The Conversation more broadly by going to donate.theconversation.com. And please rate and review the show wherever you listen. It really helps us reach a wider audience. Thanks for listening.